Hi, this is Mr. Lyons. In this last video for section 9.5, we're going to decompose a vector into two components that are orthogonal to each other. And then we're also going to compute work. So let's take a look at those two objectives. Here's some typical pictures that we would see when we're decomposing vectors into orthogonal components. For instance, up top left here, maybe a physics problem where we have a mass on a ramp and we want to find the orthogonal components of the weight vector, if you will. One component we want to be parallel to the ramp, representing the force, if you will, to maybe push or hold that mass at its location on the ramp. And then a second component of the weight vector F2 that is orthogonal to the F1 component, or perpendicular to it. A couple more pictures down here. It shows, for instance, vector V in blue being decomposed into orthogonal components, one component being parallel to vector W, and the other being perpendicular to vector W. We have a handy-dandy formula here for finding a vector projection of one component of a vector onto another vector. For example here, if we wanted to project a component of vector V such that it's parallel to vector W, that component that's parallel to vector W we could calculate with this first formula, V dot W divided by the magnitude of W squared, and then we take that scalar times the original vector W. And then down here at the bottom it says that we could, if we find V1, which is a component of V, then all we need to do is subtract that V1 from the original V to find the other component, V2, which would be orthogonal to V1 and subsequently to W also. Alright, so let's take a look at an example. So in this example, they want us to project V1 onto vector W, so that V1 is parallel to W, and then find also V2, which is orthogonal to W. Let's try out some graph paper this time here. Okay, so I'm going to just write down the vectors that we're working with in the example here. We have V is equal to I minus 3j. And we have W is equal to I plus j. And I'm going to go ahead and graph those here on the left side. On the rectangular coordinate system. So we have I, V is down here, the terminal point is here. Oh, come on. There we go. And then we have W, which terminal point is at 1, 1. Here's W. And so, using our theorem here, we can find the component of V that is parallel to W by taking the dot product of V and W and dividing that by the magnitude of W squared. And then we're going to take that scalar, if you will, and multiply it times the original vector W. So dot product is just the horizontal components of the two vectors multiplied together. And the two verticals, -3 for V and 1 for W, and then adding those two products. And then down here we've got our magnitude of W, which is going to be our horizontal component squared, plus our vertical component squared. And then we take the square root, but we're going to square that magnitude, so that cancels the square root. So all that good stuff is our scalar multiplier of the original W vector, which is just I plus J. Okay, so simplifying, we've got -2/2 as our scalar, and then we're multiplying that times I plus J. So our V1 vector ends up to be just a -I minus J. To find the V2 component, which is perpendicular to W, we're just going to subtract V1 from V. So V2 is going to be the original vector V minus V1. So we're going to subtract the horizontal components of the two. Put this in brackets, so we've got our 1 for V, and our V1 component, the horizontal component, is -1. So we're going to subtract a -1. And that's going to be our I component of V2. And then plus, we're going to subtract our V and V1 horizontal components. So our V had a vertical component of -3. And our V1 is, we're going to subtract a -1 here for, that's the vertical component of V1. So that will give us our vertical component of V2. And so simplifying here, we end up with V2, which is T2 times I minus 2 times J, or 2J. And let's go ahead and draw those up here to make sure that they make sense. So our -1, -1 is V1. So that's out here, parallel to W. And our V2 is 2, -2, so that would be out here, fourth quadrant. And so here's V2. And certainly if we dash in the components of V, it looks like we've done that correctly. Alright, so let's go on to computing work. So in physics, work is just the magnitude, or I should say the constant force F vector, which has a magnitude of F, shown in the formula here. And we got to take that times the distance that we move the object. So the distance between A and B, for example, would be the magnitude of vector, or the distance vector AB. Well, we can also calculate work by taking the vector F and dotting it with, or doing the dot product with, the distance vector AB. So let's try that out in an example. So here we have a girl pulling a wagon. She's applying 40 pounds to the handle. So that's going to be the magnitude of our force. Let's write that down. Magnitude of our force is 40 pounds. And our distance from A to B, if you will, is going to be 200 feet along the ground. So we're going to go ahead and say that the magnitude of AB is 200 feet. Okay. And so I suggested that work could just be calculated by taking the dot product of two vectors, the force vector, dotted with the distance vector. Okay, so how do we write when our force is along this handle, which is 30 degrees with respect to the ground? How do we write that vector, force vector? Well, remember our x component is just the magnitude of the vector times the cosine of the angle, and the vertical component is the magnitude of the vector times the sine of the angle. So we can actually, they've already dotted in horizontal, I can dot in vertical right there. Okay, so let's write that. So we're going to end up with here, work is equal to our 40 cosine, magnitude of the force times the cosine of 30 degrees. And that's our I component, and then we're going to add to that the 40 sine 30 degrees, and then that's our J component for F, and then we're going to dot that with our AB vector, which is just has a horizontal component, doesn't it, of 200. So that's 200 I. And so when we dot this, we've got our 40 cosine 30, and we're going to multiply that times the other horizontal component of the other vector, or the AB vector, which is 200. And then if we look at the multiplying the vertical components here in our dot product, we note that the AB vector has a vertical component of 0. So we're just going to end up with 0 for the second product here, aren't we? And so our work then is going to be our 200 times the 40, or 8,000, times the cosine of 30 degrees. And the work then is 8,000 times root 3 over 2. Or 4,000 root 3. And the units are feet, pounds. Okay, that's it for this video. See you next time.